Hello, my name is Ariel Ortiz. You can call me Ariel. I work at Tecnológico de Monterrey, the Monterrey Tech back in Mexico. And today I'm going to give a talk titled The Dawn of Lisp, or How to Write Eval and Apply in Clojure. Okay, let's start talking a little bit about me. First of all, I'm an educator. You can see in these photographs, in the upper one, this is the university that I work at. We're located north of Mexico City. And the one beneath is a photo of myself and my class programming language course that I'm teaching this semester. This is a class in which I'm currently teaching using Clojure. And I'd like to say hello to all my students that hopefully will be looking at this video later on. I'm a language geek, okay? I really like programming languages. Since I started programming, that's what I really enjoy doing best. In my classes, since I started actually teaching, I've taken into account that I think I've used somewhere around 18 different high-level programming languages in all almost 3 decades I've been teaching. I actually started using a little bit of Common Lisp when I was an undergraduate student, but I sort of didn't get the hang of it. But it wasn't until 1994 when I actually went to a conference on using Scheme in education, and I got the opportunity to hear there to listen to some talks by Daniel Friedman from Indiana University, by Robert Cartwright from Rice University, and this other guy called Ian Ferguson from a company called Schemers Inc. And they really sold me the language. They really convinced me. I sort of had a religious conversion at that point, and I started using Scheme in my classes that same year in 1994. I discovered Clojure somewhere around 2009. I think it was probably in some forums in Reddit. I read about it. I was using a lot of Java in that time, so it made a lot of sense to start using Lisp together with a Java virtual machine. So that's why I started using Clojure. In 2011, I incorporated Clojure into my programming language course, and I've been using it since. So we're going to talk today basically about 2 things. First of all, we're going to give a very brief introduction of the origins of Lisp. Maybe some of the details that I'll be explaining are familiar to many of you. And then we'll spend a little bit of time, the rest of today's talk, explaining how we proceeded to implement a Lisp interpreter using Clojure, very much modeled around one of the original definitions of this language. So it starts with John McCarthy. Okay, he was working at MIT, and he published in the April issue of the Communications of the ACM in 1960 this paper called Recursive Functions of Symbolic Expressions and Their Computation by Machine, Part 1. John McCarthy says that he planned to write a second part, but he actually never did it. Okay. Here he explains actually what this Lisp programming system is about, how it could be used to program recursive functions. At that time, languages that were available, like Fortran, usually did not support recursion. So this was a novelty. And basically, what McCarthy wanted to do was to incorporate some of the ideas that Alonzo Church had explained in this other book. Alonzo Church is an American mathematician that in 1941 published the calculi of lambda conversion. So basically he expressed here how to represent or use functions to do computations. You might remember that Alonzo Church worked also in a few years before that with Alan Turing, and they got to the conclusion that the Turing machines, the universal Turing machine, were basically equivalent to the way that he was proposing to use functions. Okay, but McCarthy actually, well, basically discovered or wanted to propose that it was much easier to think in terms of functions or using functions instead of using the Turing machines, which were a little bit more complicated to use, at least even in a conceptual level. So McCarthy actually carried out to take his ideas and make them run in the IBM 704. So his plans were to actually have a running compiler for this mainframe computer. Remember at that time, most computers actually ran using punched cards. So you would actually have something like this. Not really sure if this is real or if this is just a joke. Okay. But notice here in the upper part of the punch card, it has a bunch of closing parentheses. I mean, in current systems, putting more closing parentheses than required would typically produce a syntax error in your code. But I don't know if this was valid in those systems, in the Lisp systems of the time. So, well, it says here you can tell the Lisp programmers, they have pockets full of punch cards with closed parentheses on them. Okay, once again, I'm not really sure if this is a joke or if this was serious, but even those, at that time, first systems were programmed in Lisp using punch cards. Okay, Steve Russell was also working at MIT. I'm not too sure if he was a student or he was working in some other manner at MIT, and he saw one of the drafts written by McCarthy explaining how Lisp should actually work. And he saw the formal definition, and it said, well, this could actually be programmed in the computer, and he took it into account to actually develop and program the first Lisp system as an interpreter. Basically, McCarthy told him that that was not the purpose of his formal definition of the language, but it was an interesting exercise that he took basic formal definition and converted it into a program, and this is really what makes this definition fairly interesting, fairly neat. So Steve Russell, you might remember him. He was one of the co-authors of Space War, which was one of the first video games that were available. You can see here in this photograph a terminal that was actually running Space War. This, I think it was a PDP-1 running there. So Steve Russell also had a hand on implementing this game and implementing the first version of a Lisp interpreter. So somewhere around 1962, this manual got published by MIT, written by John McCarthy and some other people. And the interesting part of this programming manual is that it had section 1.6, that was titled a universal Lisp function. And basically explained here in a formal notation how we could define basically Lisp in terms of itself. This is actually about the bottom half of page 13 of this manual. And if you happen to be able to look at the details, you can see that this is not using S expressions. It's using something that is called M expressions, or meta expressions, that were basically like the ideal notation that John McCarthy wanted to use for his language. But for simplicity's sakes, it was later converted into S expressions that uses basically parentheses, as we know in most Lisp dialects. Okay, so you can see here in the upper part, I don't know if you're able to read it, it says eval quote. This was the startup function. Okay, everything in theory started from here, and this one called apply, and this one called eval. Okay, so as you can see, there are two main functions over here, apply and eval. There's some auxiliary functions here. Okay, but that basically was the full definition of the language in itself. This is not necessarily meant to represent the first implementation, but basically it gave, in a formal notation, it gave an idea of how you could implement Lisp using the same notation. Okay, so this is really what we're going to be working with. It's really interesting to note that Alan Kay, who is the author of the Smalltalk programming language, and later on, 2003, he was the winner of the ACM Turing Award. He basically had this to say about the piece of code that we saw, or the formal definition that we saw just a moment ago. It said, Lisp defined in terms of Lisp. These are Maxwell equations of software. I remember the first time that I actually saw this quote about this interview that Alan Kay had a few years ago. And when I read it, I'd say, wow, that must be something if only I knew what Maxwell equations were. Okay. So I checked those out in Wikipedia, and this is the image that you see, the equations that you see here. Yes, I discovered that they had to do something with physics. These are a set of partial differential equations that are basically the foundation of classical optics and classical electromagnetism, quantum field theory, and electric circuits. So I don't really understand them. I feel a little bit ashamed of this because I'm an engineer by training, and I don't know if I slept over in my physics class when they explained this, but I don't remember actually ever hearing about Maxwell equations. So in general, what these equations say, science, okay? So basically it's a big deal, even if we don't necessarily understand it, okay? So let's quickly review how eval and apply work in Clojure. So we're going to be talking about these two functions, so it makes sense to actually understand how they work. Eval, you send a piece of data, okay, in this case a list, okay. If you see it, the list is actually quoted, so it's not evaluated. This list can be produced whatever way you want, okay. It's a processed and a full piece of data in Clojure, and once you send it to eval, well, it proceeds to evaluate it, and it gives you the corresponding result. Interesting thing here is that this list could have been created using cons or any other operation, and at the end you just send eval and it works. Okay, this contrasts how eval works in other languages. If you used Ruby, Python, or JavaScript, all these languages also have an eval function, but they usually just receive a string. Okay, in the case of Lisp and Clojure specifically, you have to send a full valid data structure, okay? You can't send a string. I mean, you can send a string, but it evaluates just to that string, so not very interesting. And apply might look a little bit similar, okay? Apply in its simplest form. It takes two parameters. The first one is the function that we want to apply, and then it takes a list with the arguments that we want to send to that function. Okay, so this also gives us 4. The apply form in the apply function in Clojure is a little bit more elaborate than this, but this is the simplest way that it can actually work. Okay, so it's an alternative of using the traditional way of calling a function, which is opening a parentheses and then specifying the function that we want to call, and then the parameters. In this case, we have a function that allows us to call a function. In certain contexts, this can come in handy. Okay. Before we go to see the code of the interpreter, let's just mention how memory locations work in the 704 mainframe, IBM mainframe computer. A register at that time really meant a memory location, okay? And it's basically what we would call a word right now. It was composed of 16 bits, okay? 15 of those that were could be referred as the contents of the address part of the register number, and contents of the decrement part of register number. Notice here that the word register refers to a memory location. It's not what we currently understand as a register, a part of the CPU, okay, where we store information for very fast access, okay? Here, when we're calling or we're referring to registers, it really means memory location, okay? So we had 15 bits for the CAR, the car, and 15 bits for the CDR, okay? Remember, the address and the decrement were not necessarily, they were actually not registers, okay? They were just a part of our words in memory. And we also had other 3 bits for the prefix and tag that were used for some other complicated operations to index our memory stuff. This is more or less how this could have looked in an older system. Here we had a bunch of memory locations. Each of these rows is a memory cell. We would call them now cons cells because whenever you call cons, this is what the function actually returned. Okay, so a singly linked list like this one, okay, could have been represented in memory something like this. You would actually have a root binding here, okay, referring that this list started in address 103. So in address 103 here you have A with in the car part of the console, and in the cooter you would actually have the location where this continued. So this follows in location 105. So here's location 105, and here you have a B, which is the one we're displaying here, and then we would continue in the cooter of this location in 101, and finally when we find a nil, we represent it with this diagonal line here. This means that the list was actually ended, okay? We also had another list, which we call the free list. Oops. The free list represented another list that was with contained all the cells that we had available, okay? So any time that we actually called cons, the free list, we basically returned what we had in front of this list, and we updated the reference to free to the next element in that list, okay? Here, what you see in gray, these would be actually cells that were no longer accessible from our program, so they could be at some point recycled. So the original paper that McCarthy wrote said that there was a reclamation cycle, okay? And he later explained that he used the term reclamation cycle because the term garbage collection, although it was already used at that time, didn't seem so like worthy of a scientific article. So they decided not to call it garbage collection at that point, okay? But that's how informally most people knew it, okay? So when the free list actually gets totally consumed, okay, we typically stop the world at that point, and in this first system, there was an algorithm called mark and sweep that was actually carried on, which consisted basically in reviewing all the cells that we had available in our memory, and we had to mark all of those that were directly or indirectly accessible using our available variables or bindings, local bindings or global bindings that were still alive, and we marked them all. They basically marked them changing the sign of the word, and once they did that, any cell that wasn't marked was actually integrated into the free list so that it could be used again from whenever we actually called cons again. So this is how this looked more or less, okay? It's worth mentioning that garbage collection, or the recycling process, took several seconds, okay? So at that point, it seemed like interesting to see that this algorithm was taking place, but is usually very inefficient in practical terms. It took quite a long time to actually execute. So let's talk now about the rules that we're going to be using to convert the Lisp 1.5 specification, okay, into Clojure. So basically, I translated what you saw just a moment ago, the code that we saw, or the formal specification that we saw a moment ago. I translated into Clojure following these specific guidelines. First of all, I needed to convert all the M expressions into S expressions. We'll see that just in a moment. Okay, I maintained basically all the definitions that we had, trying to make them as similar as possible to the original. So every time I called a certain function, I tried to use the same function or something very, very similar. Okay, so basically I tried to do the most faithful conversion that was possible using Clojure. The original implementation uses dotted pairs, something that we don't have in Clojure. I'm going to explain that in a moment. So we needed to take those away because we don't have them in Clojure. And also, I added a $$ prefix to all global identifiers, to some constants and some functions, so that we can quickly identify them as something that we're doing as part of the implementation. Strictly speaking, the $, according to the Clojure documentation, this is only used when you're referring to an external Java class that happens to be a nested class. Okay, so I'm sort of using the $sign in a way that is not compatible to the way that Clojure says that we should use it, but it works. I hope not to break anything in the future because of this decision. Okay, and finally, I added some white space to make the code a little bit more legible. So the definition, the formal definition that we just saw a moment ago is very, very compact. I took the liberty to make this, to add more space to make it a little bit easier to understand, okay? So we have here M expressions and S expressions so that you can see the difference. So when we call a function, we use something like this, f, then we open a square bracket, 1, a semicolon 2, semicolon 3, and then a closing bracket. This, as an S expression, is a normal Lisp way of expressing it. So we would have f1, 2, and 3. We use spaces, we don't use commas, although technically Clojure does allow you to use commas because they're basically equivalent to white spaces. If we were referring to a conditional, okay, here we have two clauses in our conditional. These are actually verified from left to right. We check the first one. If the expression that we have here happens to be true, we return whatever follows this little arrow, okay? If this expression happens to be false, okay, we go and analyze the following clause, or whatever, how many clauses we have left. In this specific example, here we have t, which is a special symbol that represents the truth value. So this is like a default or an else clause, which if none of the previous ones happen to hold true, this one will, okay? And this is how it looks as an S expression, okay? So we have the use of cond, and the clauses are included in parentheses, and then we have the condition and the resulting associated value. About dotted pairs, here, this is something that you can do in many Lisp dialects. You can do a cons of something that, well, any piece of data with something that happens to not be a sequence or a list, okay? So what happens here is that you get a dotted pair, okay, which graphically you can imagine something like this. The car and the cooter, or the first or the rest, happens to be, in this case, a symbol. You can't do that in Clojure. Okay, so whenever we do a cons of two elements, if the second element happens to not be a list, we actually just place it as if it was the second element of the list, okay? So this is a provision so that our code works well in Clojure. Okay, so we have some simple definitions in the code, okay? All this code is available at GitHub. I'll give you the link at the end of the talk. So if you want to see it in more detail, you will be able to. So for example, in the case of the $t, this is something that represents true. If we check the code here, the definition is very straightforward. Okay, so $t represents true, okay? And the same thing happens with the rest of the definitions that we have here. This $f represents false. This $nil represents the empty list. This $cons is the provided, or the equivalent of standard cons operation, but this one can allow you to cons two symbols together. Atom is a predicate. It returns true if the given argument is an atom. Atoms, it's worth mentioning here, don't have anything to do with the Clojure reference type atom. These are very old traditional atoms, basically saying, well, anything that can't be divided is an atom, so symbols were atoms. Also, the empty list was considered an atom. Anything else was considered to not be an atom, okay? So this returns true if it's an atom. If it's not, returns false. Equal, EQ, was used to compare two symbols. If they are the same, it returns true. If they're not the same, it returns false. And we had null. Okay, notice that I'm not ending these with question mark, even though they're predicates. Null returns true if the argument is an empty list, false in other cases. And once again, I decided to use the same names as much as possible, just with the $, as much as possible than the original specification, okay? Then we have car and cooter. These represent basically, as we saw, the first in a cons cell, the car represents the first part, the cooter the second part, okay? And we had actually some combinations of these, okay? So whenever you see, for example, this last one, this represents the car of the cooter of the car of your argument, okay? So a lot of scheme and common Lisp users really like this possibility of combining car and cooter in just one operation, and they usually say that that's why they do not like using first and rest as we do in Clojure. I personally like first and rest more. I think they're much easier to understand. But I'm keeping these names just because I'm trying to be faithful to original publication. And if you look at any of these, for example, car maps directly to first, okay, cooter directly to rest. And for example, this last one, I use the composite Clojure function to do first the car, then the cooter, then the car, okay, in the same order that we have here. But just remember, these are actually applied in the reverse order in which we read them, okay? So instead of doing first the car, we do first this car, we first do the last one, okay? We have some more elaborate definitions, okay? We have, for example, this thing called cond. This is my version of cond, and basically this is a macro. It really wasn't required, but once again, I did this for the purpose of maintaining the original syntax. The cond in Clojure doesn't require, and actually would be a syntactic error to add these levels of parentheses here, but the traditional or the standard definition in Lisp 1.5 required actually to put each clause in its own list, okay? So I'm using this one to return to that original syntax. Once again, I know that this might seem fairly ugly to many, and once again, I did this just to maintain it as faithful as possible. And this is a macro that just converts this into its equivalent if. So it actually works fairly similar to standard cond in Clojure, but it requires that extra group of parentheses just to maintain the spirit of the original definition, okay? Then we have this thing called perilous. Okay, this creates a list of pairs. So allow me to just demonstrate how this would actually work. So if we have here perilous, you would actually send two lists here. The first one would be a list of symbols that represent variable names, and then the second would represent a list of values, any values, and it would actually receive, a third parameter that actually represents an existing list of pairs that already exists. Okay, so this function, as you can see, pairs this symbol, which is going to represent basically a variable, to its value. So x goes with 1, the y goes with 2, the z goes with 3, and the rest of the list is basically the same thing that we send over here. Okay, so this is going to be useful when we pair together the formal parameters of a function with their actual parameters, okay, or the arguments. Then we have this other function called assoc, okay? This works to get an element from association list. We're going to be using association lists a lot in a moment. So you use it like this. You put assoc, you put what you're looking for, and then you specify a list containing pairs, like the list that we obtained in the previous as a result of the previous function. So let's say that you had an association list like this, okay? And here we're saying I want to look for the key x, okay, in this association list, and hopefully it will find it, and it will return the full pair, including the key and the associated value, okay? If you try to find a variable or a binding that does not exist, the result is actually undefined. Explicitly, what happens here is that it produces a Stack Overflow because it never assumes that we actually can have an empty list at the end. Okay, so you shouldn't actually try it without with a symbol that doesn't exist in the association list. Okay, so this, in other words, this works similar to, in spirit at least, to a Clojure map. Okay, so we're just trying to get the associated key and value in a group of pairs. Okay, so that's what a sock does. The next function is called fcon. Okay, this is an evaluation of the condition. So this one works like this. Okay, you specify fcon, then you send here a list of clauses. Let's say that we have 2 clauses here. The clause can have something like an expression like this, atom A, and if that's the case, let's say that we return quote yes. That would be the first clause. Second clause would be, let's say, true. And if that's the case, let's quote no. Okay? So this is, imagine that it's a cond, taking the cond away. So here we have the first clause. Here we have the second clause. And we want to evaluate this in a certain context or environment. Okay? And the environment is just this association list that we've been looking at just a moment ago. And we just need to indicate what the values of the variables that we're using are. So we're using an A here. So let's say that A happens to be the symbol X. And we also need to define T. T has to be equal to a true value. Okay? So we evaluate this, and it says yes. This means that A, this symbol X, is an atom, so it returns quote of yes. But if this happened to not be an atom, for example, if we put this inside a list, okay, it now should return us no, okay? So that fcon basically does implementation of the evaluation of the different clauses of a condition, okay? And we have this thing called EVlist, which is evaluate list, and this one is going to be used later on to evaluate a list of expressions. So for example, let's say that we say I want atom A here as a first expression, and as a second expression, cons of B and C. Okay? So this is a list of expressions that have not been evaluated so far, and I'm going to provide here an association list that says A is equal to atom X, and B is equal to atom Y, and C is equal to the list WZ, okay? So we evaluate this, and as you can see, atom of A, because A is the symbol X, is returned as true, and cons of BC, if B is Y and C is WZ, it actually returned a list with Y, W, and Z, okay? So EVlist allows us to take a list of expressions, and it will call our eval function, okay, using whatever association list with variables we provided, okay, and it will one by one evaluate this. Once again, this is going to be useful when we look at the implementation of apply and eval, because in some moment we need to evaluate all the arguments that are sent to a specific list, okay? So let's proceed to see now these two functions, apply and eval. We're going to see them with a little bit more detail. So here, if you look at the apply, let me show you first the code. Okay, once again, these are the functions that we saw in the formal definition a few minutes ago. Okay, so you can look at this. I'm going to see clause by clause basically, because it's a little bit complicated to understand at first the code here. So first part is going to take care of seeing if, remember, apply takes first a function and then a list with the arguments, and then an additional parameter here that represents the bindings, the association list with the bindings that we want to take into account. So first thing, we're going to check if fun is an atom. If it is, we're going to check if it's the car, the cooter, the cons, the atom, or equal. And if it's not an atom, then we're going to check if it's a list containing a lambda as a first element, or a label. We're going to see that label is going to be useful to define recursive functions. Okay, So if we look at this quickly, car of this, okay, assuming that my list of parameters are this, okay, so here to implement car, we just need to return this element here, which we obtain with the car of x, okay? Some in a similar way, okay, this is how we can implement cooter and how we can implement cons, okay, here we call our own implementation of cons with these two values. I'm using here the colors when I say car of x, and I put something in the same color here. This is what, in this specific example, that what we would actually be getting, okay? And whatever we see there in blue means that's the final result, okay? Then we have here atom, EQ, and any other symbol. This is the way that they actually get implemented. Once again, you'll have a chance to look at the code if you want to, or look with a little bit more tranquility these slides also as well. The interesting part here happens when you have a lambda expression. Okay, here when you find a lambda, okay, you evaluate the body of the lambda and you create a list of pairs taking the parameters, the formal parameters, and x, which would be our list of arguments. Okay, so we bind these together and we append them to our associative list that we had before. Okay, so that's how lambda gets translated. And specifically label, okay, label was actually introduced because we want to have a recursive call, so we want to make use of the same function, so we create here what is a label. And basically what this does is that it extends our associative list. I'm sorry. The associative list that we have here, okay? And we have the A at the bottom, okay? And we add a pair with the name of our label and the body, well, or the lambda in this case, that we're joining here together, okay? So we're adding basically that symbol, that binding to our list of bindings or our association list, okay? Then we have here the implementation of eval. Eval, if you send a variable, it looks for that variable in the association list, so this is where we call a sock, okay? If you're implementing quote, this is very straightforward. Remember here, eval is going to be taking care of special form, so basically it takes care of the lookup of variables about quote, and in this case we only get the value that we care here without any further evaluation. And we also have here the cond, which just calls the other function that we just defined a moment ago, the fcon. Okay. The last part here done in eval is when we call, actually the second to last part that we need to do here is when we have the first element of E is a symbol, but it's not quote or cond. So here we delegate this to apply, which actually knows how to do that. We get that first symbol as the function that we want to call. We do the evaluation here of the arguments, and we send the same associative list to apply, okay? And now finally, the last part that has to do with eval. Here in this case, we know that E is a list, okay, but its first element is not a symbol, so should be something like a lambda or a label. Well, what we're going to do here basically is call apply with the car of V, which is the thing that we have in red. It's a lambda or a label. And we call the EVlist with the cooter of V, which is what we have here in green, okay? And we do the evaluation of those parameters, and we send that together with A. So let's, we're almost out of time, so let me just do a few quick examples here. So if we want to check how eval works in its very simple way, we would actually call car, for example, here of a list L, and then specifying in the associative list, okay, that L is a list containing whatever symbols you want, okay? And this has to be quoted as well. Okay, so car of L being this is A, okay? No big surprise there. If we try, let's say, cooter, okay, we get the cooter of L, okay? let's see something a little bit more complicated. Let's say that what we receive here is a lambda expression. Okay, this lambda expression is going to take x, cons it to another list with x, and with nil. Okay. And what we're going to do here is send the corresponding list of bindings, and here we're going to say that nil is the empty list. Okay, so that's our bindings, our list of bindings. Okay, and let's see if this works. Oops, I'm sorry. I needed to, I'm sorry. I'm missing lambda receives a parameter. I'm skipping that, sorry. So here we would specify, for example, let's say quote of A. Okay, so now it gives us AA. Quote of A was the value for the parameter x, and we just cons that A to the cons of A of nil. Okay, and let's do last example, because we already ran out of time. Let's say that we now want to check how a label works. Let's say that we want to implement this function called mapcar. Mapcar is actually like map, the ordinary map function that we know, okay? But it was originally called mapcar. And here what we're going to do is we're going to say this is a function, okay, that receives two parameters, a function and a list, okay? And the only thing that we do here in this lambda is define a conditional where we're going to check first if the list is equal to nil. The list L is equal to nil, and if it is, we return nil. There's nothing else to do here. And otherwise, okay, we put a true here. We're going to cons the result of calling f with a parameter car of L. Okay, and we send here the recursive call mapcar of same function f, but now with the cooter of L. Okay, so hopefully this should be an implementation of map. We need to specify here the parameters that we want to use. Let's say that we have a function called dupe and a list called lst. Okay, so the only thing that we need to do here is provide the bindings. So dupe is going to be basically the same function that we had just a moment ago. Cons of x, and nil. That's the first binding. Second binding is the value of list. Let's say that we have the list A, B, C, and D. And the value of nil is the empty list that we use. And the last binding that we need is true, which needs to be bound to true value. And as you can see, this is the answer. We applied the function in the label to this, okay? A, B, C, and D, so it duplicates each of these elements, okay? So that was a much more elaborate example here, okay? So hopefully that would give you a good idea of how this actually works, okay? Thank you very much for your attention. And if you want the slides and the code, you can check this here or use the QR code here. Thank you very much.